time has come to move along on our tour of matter by phase. We've covered the behaviors of gases and liquids so far, and we've seen how the nearly ideal behavior of gases leads us to formulate general laws that describe the behavior of all gases fairly well. We've also seen how the close contact of otherwise freely moving molecules in liquids gives them certain properties in common with one another, most notably their defined volume, which leads to a lack of compressibility. But we can't leave solids out of the discussion for long, and this lecture begins that process of bringing solids into the conversation. We're about to start a journey that will survey the most commonly encountered solids, most notably pure metals like gold, alloys like bronze and brass, ionic solids like the salt on your dinner table, and network covalent solids like diamond and glass. It's a journey that will take us 2 lectures to complete, so we better get started. We know that solids have defined volume and shape from our everyday observations. But what is it about solids at the atomic and molecular scale that gives them that property? Of course, by now we know that the reason for this is that the molecules, atoms, and ions that make up solids are locked in place by attractive forces so strong that these atoms, molecules, or ions lack the kinetic energy to overcome those forces. When this happens, a new consideration arises. Because their molecules, atoms, and ions are locked in position within them, solids can be highly ordered. And when they are, we call them crystalline solids. And their high degree of order means that many of them have remarkably regular structures for us to study. There are 2 terms that we have to define very well before we can go any further. Those are crystal lattice and unit cell. A crystal lattice is best defined as repeating geometric arrangement of atoms or molecules in space. Take a look at this representation of a few gold atoms in their crystalline form. Notice that this solid has a highly ordered repeating structure. Gold atoms aren't simply mashed together in random positions. No, their locations regularly repeat, creating predictable patterns in the array of atoms. This arrangement is the crystal lattice of gold. But if crystal lattices go on and on forever, how do we draw one? We don't have enough ink, paper, or time to draw the lattice. Even if a crystal were so small that it would fit in our hand, it would still take us forever. But the repeating nature of the lattice makes this an easy problem to solve. We can simply discuss what's called a unit cell. A unit is the simplest repeating arrangement of atoms that can describe a crystal lattice unambiguously. And this is best demonstrated using some very simple artwork. Let's take a look at a very famous painting, one done by the renowned artist M.C. Escher. Escher was famous for doing a lot of really interesting eclectic paintings, but one of his more famous styles is to tessellate objects, and that's what I've done here. As you can see, I've put up one of his more famous tessellations, in this case, birds that all fit together perfectly, right up against one another. Now, what's more important than the fact that they're touching one another at all sides is that there's a repeating pattern in this artwork. So, if I wanted to reduce this artwork to the minimum size necessary for someone to reconstruct it later, how much information would I really need? Let's say that I take this fraction of the painting. From that fraction, could I reconstruct the entire image? Well, of course, in this case, I could. Right? I simply take 4 of them, overlay them appropriately with their edges touching. I've recreated the entire work. But I don't need a cell quite that big. Let's try again. Let's get an even smaller slice of the painting. How about this one here? Can I reconstruct from this? Well, in this case, I can do it as well. All the information necessary to recreate the entire work is contained in this smaller cell, this smaller piece of the artwork. Yet again, I can take an even smaller slice at this point. I've got just this tiny little corner here. And from that, if I place multiple pieces of that corner together, I can recreate the image. But what happens if I try to go even smaller? At some point, I reach this condition at which I have a slice of the diagram or the image that doesn't contain all of the information that I need. Notice that in this box that I've drawn right here, I'm missing the right-hand wing of one of the white, and I'm missing the head of one of the whites. That information is gone. And without it there, it's impossible to completely reconstruct the original image. So that smallest possible slice of the image that we actually can use to recreate it is what we would call the unit cell. So, unit cells don't necessarily have to apply to tessellations either. Think about this. Let's do a little cleanup in the lab here. Let's say I'm stacking glassware in a slightly unconventional way, but here are a series of Erlenmeyer flasks stacked together. They create a pattern, don't they? There's some empty space in my pattern, but that doesn't matter. It's still a repeating pattern. I can recreate my repeating pattern if I communicate just that minimum amount necessary. In this case, here it is. This is a unit cell for my stacked glassware. It contains all the information I need to create both the upright-facing and the downward-facing Erlenmeyer flasks. So, from just that little slice, I can recreate the entire image. Now, so far, all of our unit cells have been square or rectangular, but that's not necessarily the case either. Let's say that I'm really talented at stacking glassware, and I create this pattern instead. That's impressive. Now, this pattern, right, we could recreate if we communicate just enough information that we can put the whole thing back together. So you may have immediately looked at it and said, I see a pattern here. If I take this slice of the image, I can recreate it and stack it together and reproduce the entire pattern. And you'd be right, but this would be too large. That unit cell is not the proper unit cell. You may look at it again and say to yourself, well, I see an even smaller pattern here that I could use. If I use that, I could tessellate those squares together and create the image again. You would also be right, but again, it would be too much information. It's more than you actually need. All we really need in this case is this. Just this small slice containing 2 of our flasks. So how does this come together to form the entire image? Well, it doesn't come together in a square or rectangular pattern. Instead, it comes together in a very interesting pattern that we call hexagonal. In this case, if I rotate the unit cells and stack them appropriately, I can recreate the entire image. So, unit cells need not be necessarily square or rectangular, but can also be interesting shapes like this one here, this parallelogram. If we can manage to do the same thing for a unit cell at the atomic level for any given crystal, then chemists can simply recreate the structure of the crystal by tessellating those units together, just like an M.C. Escher drawing. Now, probably the best way to begin to understand how the symmetrical arrangement of atoms can impact a material is to consider one of those materials. Metals are so common in our lives. Everywhere we look, we see them. In our homes, our vehicles, our hospitals, even in nature. Examples of metals are all around us. They make up about 3/4 of the elements in the periodic table. So, naturally, they're well worth understanding. Metals are some of the most useful of all the elements because of certain properties that they all share. They all conduct electricity. They're all malleable to one extent or another, meaning that they can be bent or molded into shapes and pulled into wires to satisfy their intended purpose. Their abundance in our world even led to the ancient Chinese culture suggesting that metal itself was an elemental substance. Of course, we now know that metal itself is not an element, but many elements are in fact metals. But all of those metals aren't created equal. They may have a few similarities, but the minuscule lithium atom compared to the massive radioactive actinide series elements will differ, and they offer a menu of elemental compositions unrivaled by any other type of chemistry. Though nearly all of them are solid at temperatures we commonly experience here on Earth, there are a few exceptions, most notably mercury, which is a metallic liquid, still electrically conductive, but able to flow. Now, this property has led to the frequent use of mercury in contact switches that can sense motion. But nearly all other known metallic elements are solids at standard temperatures and pressures. Some are notably soft, like copper, which was adopted early in human history because of its availability as a native metal and the ease with which it could be fashioned into weapons or tools. Other metallic elements are incredibly hard, like titanium and chromium, famous for their durability and favorites in military and flight applications where toughness really counts. We've already discussed how the phenomenon of metallic bonding occurs. We saw how atoms of metals come together and form closely packed clusters with a valence band that allows the valence electrons of those atoms free run of the entire matrix. But during our bonding lecture, we only looked at a small two-dimensional representation of those closely associated atoms. And we didn't really take the time to carefully consider the geometric arrangements that metallic atoms can take on when they come together to form that metallic solid. This lecture is going to remedy that, as we look very closely at the arrangement of atoms in solid metals. We're going to get some real-world metals into the discussion in a moment, but for now, let's consider crystal lattices and unit cells in general, using a simpler two-dimensional representation of what might be atoms in a lattice. Unlike the creations of M.C. Escher, we're going to be working with spheres, a shape that is genuinely impossible to tessellate. We already know from our discussions on the structure of the atom that atoms aren't really spheres. They have very complex structures and geometries within them. But let's assume for just a moment that they are, because this assumption actually works very well for what we're about to investigate. Now, when we want to pack spheres into space as efficiently as possible, there are a couple of different arrangements that we could try. Let's try two of the most commonly observed. One is called square. Now, in the square style of packing, we get this kind of arrangement. You'll notice that I have vertical rows, right, and horizontal rows as well, of these atoms all stacked together nice and orderly. And the unit cell here is very easy to identify. In this case, it's right here. It's the centers of adjacent atoms creates the unit cell. And this is very clearly square. So when we take a look at the actual measurements of the unit cell, we expect to find that the lengths A and B are equal and that alpha is 90 degrees. And this is in fact the case in a square two-dimensional unit cell. But take a close look at this square unit cell here. Notice these large diamond-shaped areas here where there's empty space. These spheres are touching one another, sure, but they're not packed together as efficiently as they possibly could be. Let's take a look at a different arrangement and see if we can illustrate that. Here is our square unit cell again. Now I'm going to make a slight change, so watch carefully as I shift the atoms inside of this cell here. Do you notice something? There's a lot less empty space here. As I slide these over so that they rest within the well created by the layer beneath them, I significantly decrease the unused space. And so my packing is far more efficient in this, what is known as a hexagonal unit cell. Now, the hexagonal unit cell actually looks like this. It's a parallelogram. And that parallelogram has very specific dimensions. And those dimensions are equal values for A and B, as well as alpha being 120 degrees exactly. So naturally, that begs the question, if the unit cell is a parallelogram, then why am I calling this hexagonal? And the answer to that is, when you look closely at the arrangement of these atoms down here, choosing a central atom, what you'll notice is that it has 6 neighbors within this two-dimensional structure here, creating the outline of a hexagon when we look at it from that perspective. So don't let that one catch you. That's a big gotcha here. The hexagonal unit cell actually has a parallelogram-shaped unit cell, and a hexagon is found when we look at it in a higher order kind of structure. So to sum up, description of a two-dimensional unit cell requires that we report on 3 things: the length of the 2 sides and the angle between them. Now, we often use that notation A and B for the 2 sides and the Greek symbol alpha for the angle between them. So when A and B are equal and alpha is 90 degrees, we have a square unit cell. When we change alpha to 120 degrees but keep A and B the same, we create unit cells that are more closely packed together. But there are actually 3 other general arrangements that exist in 2 dimensions. And those are the rectangular, the oblique, and the centered rectangular formations. Now, in a rectangular type of arrangement here, we've got a unit cell where A is not equal to B, but alpha is equal to 90 degrees. In the oblique arrangement, we've got a situation where nothing is equal. A is not equal to B, and alpha is not 90 or 120 degrees. And we have centered rectangular, in which A is not equal to B, but alpha, in fact, is equal to 120 degrees. All 3 of these are well worth knowing about, but they tend to be found in more complex materials. Because notice that when we're dealing with a simple situation of all spheres of the same size, that all 3 of these have got a tremendous amount of unused space. They're a very inefficient way to pack spheres of the same size together. So again, well worth knowing: rectangular, oblique, and centered rectangular. Although they're probably not going to surface much during our discussion, they round out all 5 realistic possibilities for 2-dimensional cells. So the total realm of possibility in 2 dimensions is comprised of just 5 lattices: square, hexagonal, rectangular, oblique, and centered rectangular. But we're not done yet. If we're going to use this concept in the real world, we're going to have to consider all 3 dimensions. Our simple 2D representation helps us to understand the basic concept of unit cells and the great variety of symmetries they can produce, even in just 2 dimensions. But we live in a 3D world. So to properly describe crystals, we need a 3rd dimension. So let's go back and look at a square unit cell, but introduce a 3rd dimension, C, which creates 2 new angles. Those angles would be beta and gamma, of course. Now, varying the edge lengths A, B, and C, as well as angles alpha, beta, and gamma, a total of 14 distinct 3D unit cells can be created. These can be organized into 7 general classes of lattices: cubic, hexagonal, trigonal, tetragonal, orthorhombic, monoclinic, and triclinic. Now, we call the arrangements described by these 14 unit cells in 7 classes Bravais lattices. They're named for Auguste Bravais, a French physicist who correctly identified these 14 cells in 1848. When all lengths are identical and the angles are held at 90 degrees, the resulting unit cell it defines is a cube. So we call crystal lattices described by this unit cell cubic. Many metals have cubic crystal lattices. So let's focus there and consider the rich library of symmetries that even just this simple arrangement can produce. You might have noticed that the cubic unit cell makes up 3 of the 14 Bravais lattices. And you might have asked yourself, how is that possible? Isn't a cube just a cube? Not exactly. Sometimes it's not all about the box, it's what's inside that matters. See, the 3 cubic unit cells, primitive, body-centered, and face-centered, are all indeed perfect cubes with atoms at each corner. But when you look closer, they each describe a very different arrangement of atoms overall. And because so many solid metals tend to form cubic unit cells, let's look at this one class of Bravais lattices in more detail. Now remember that in a cubic unit cell, all sides are equal in length and all angles are 90 degrees. So, if I were to take 2 square arrangements of atoms and stack them on top of one another, I would get this arrangement. It's perfectly cubic in all ways. 8 atoms each define a corner of my unit cell. Now, simple, geometric, perfect, but also primitive, quite literally. This simple arrangement is called a primitive cubic unit cell. Now, the problem with this arrangement is that it produces a crystal in which each atom has just 6 nearest neighbors with which to share its metallic bond. In this arrangement, only 52% of the available space within the unit cell is actually filled by the spheres. Contact is minimized, and the effectiveness of the valence band in bonding is reduced. This arrangement, in fact, is so poorly suited to metals that only one metal, polonium, is known to adopt it. Let's try again. Take those 2 square planes of atoms again, but now pack them on top of one another, but not directly on top. Instead, offset that second layer so that the atoms rest in the spaces left by the first square layer. And again, we're going to add a 3rd layer, offset from the second and directly above the first. This creates a denser structure, but it changes the spatial relationships among the atoms. So, layers 1 and 3 are positioned directly above and below one another, making up the boundaries of my cubic unit cell. But the atoms of my second layer aren't at the corners anymore. They're centered in the unit cell, defined by the first and third layers. I still have to account for them, though. So we call this arrangement a body-centered unit cell. Body-centered unit cells have atoms with 8 nearest neighbors instead of 6. This means a better metallic bond can form. Also, this arrangement has 68% of its volume as atoms. That's less empty space. This is a significant improvement over the cubic unit cell. More contact among atoms means more stability, and we find that many metals, including all the alkali metals, adopt this type of lattice. But we can do even better. Let's reset one more time, and this time, remember that hexagonal packing makes for a more compact two-dimensional array of atoms. So let's use hexagonal layers and see how we do. Now, since we're using hexagonal layers, we can still find a way to stack a second layer in the little wells made by layer 1. Now, again, layer 3 can find a way to rest that's staggered to both layers 1 and 2. Now, the simplest unit cell in this structure might be a little bit harder to see, but if we turn it just a bit, we can see that this is still a cubic unit cell. But on each of the 6 faces is a bisected atom. So this is called a face-centered cubic unit cell. And although this means only 6 nearest neighbors, there are also another 8 neighboring atoms very close by. This increases the overall contact even more and reduces empty space. In a face-centered cell, 74% of the available space is occupied by our spheres. This is geometrically the best filling of space that can possibly be achieved using spheres. It maximizes contact among atoms, creating valence bands with tons of overlap. Not surprisingly, this is the arrangement of atoms that a number of familiar metals take, including gold, silver, copper, nickel, aluminum, and more. All of these arrangements allow us to make sense of metals, no matter which form they take, primitive cubic, body-centered cubic, or face-centered cubic. Their symmetry leads to vast networks of metallic bonds that help explain their crystalline properties. There are, of course, other lattices adopted by certain metals under certain conditions, but the rest of the world of solids is beckoning, so we really need to move on here. So, metals are amazing crystalline materials with diverse, useful properties. But sometimes, even the buffet of pure metals afforded to us by nature simply doesn't yield a material with the properties we need. For example, modern aviation engineering often calls for metals of low density but significant hardness. Sophisticated instrumentation sometimes requires superconducting materials, and marine applications might need corrosion-resistant metals to make for a more durable product. When nature fails to provide just the right metal for a given application, that's where the chemists come in. Just as nonmetals offer a potential list of ingredients to mix, forming a vast library of compounds, many metals can also be combined to create materials with all new properties. We refer to those materials comprised of multiple metals as alloys. There are 2 general classes of alloys: solid solutions and intermetallic compounds. Solid solutions are formed when 2 molten metals are mixed in just about any composition. The metal atoms may be thoroughly mixed overall, but their arrangement within the product are not highly ordered. A classic example of a solid solution, quite literally classic, is bronze. Made from copper and tin, bronze was discovered about 5,000 years ago. And what was discovered about it is that it has this unexpected property of being harder than either of the 2 metals that go into it. Now, how is that possible? Well, the answer lies in the property of all metals that gives them their malleability, or their ability to deform. It's their repeating lattice structure. A metallic solid of very pure composition will have regular planes along which no atoms are centered, only valence band electrons. And these regions make up a plane of weakness between connected atoms, and we sometimes call these planes slip planes. When a compression, a shearing, or tensile force is applied to a metal, its atoms can relocate in response to that force by moving along the slip planes, making metals moldable. Copper is a face-centered cubic metal, so let's look at just a single plane of copper atoms from that system to help us understand. Now here we have a hexagonal packed plane of atoms. The slip planes are defined by lines of atoms that can move along one another without disrupting the rest of the lattice. When copper is drawn into a wire, bent or molded in practically any other way, its atoms are moving along these slip planes in response to the applied forces. But what happens when a tin atom, or even a small collection of tin atoms in a microscopic crystal, invades the copper lattice? The tin atoms can still participate in metallic bonding with the surrounding copper, holding the metal together. However, the tin intruders interfere with the host copper's slip plane. This decreases the ability of the metal to deform under stress. This is the very definition of hardness, and it explains how a mixture of copper and tin can create a metal harder than either one alone. And this technique is not relegated to the pages of ancient history either. It's the same type of solution alloy strategy that's used to make tough but light aircraft-grade aluminums as well. Alloys can also be employed to create materials with great corrosion resistance, such as stainless steel, which is primarily a solid solution of about 13% chromium metal in iron. The chromium metal in the steel becomes oxidized more quickly than air, and this creates a tough oxide layer of Cr2O3. That's chromium 3 oxide. Now, unlike iron oxide, which we know as rust, chromium oxide is tough and fits very neatly into this alloy's surface structure, protecting the metals inside from any further oxidation. But there's a second type of alloy I need to mention, the intermetallic compound. In these alloys, a very specific ratio of metal atoms are combined into a new, highly ordered, and sometimes very complex lattice. Compounds like these often have slip planes of their own, so they tend not to be used so much for their strength as for other properties. Niobium and tin form such an alloy. This is a carefully defined complex of niobium and tin in a rather unusual cubic unit cell with 2 niobium atoms on each face of the unit cell. Electromagnets using this material for their coil can maintain extremely powerful magnetic fields with little or no applied voltage, thanks to the unique combination of valence bands within this highly ordered bimetallic superconducting crystal. Our discussion of solids is not yet over, but it is time to take a short break before continuing on and review what we've covered so far. We dove into solids today, reminding ourselves that solids are all about holding atoms, molecules, and ions together in close contact. We thought about how small structures can be packed together, and we investigated the concept of the unit cell, first using a few examples of tessellations. After that, we really got down to the business of classifying and describing how atoms might pack themselves together. We started in 2 dimensions, acknowledging that there are 5 different types of possible unit cells for a 2-dimensional array of atoms, which we modeled as spheres. But then we realized that we had to think about the 3rd dimension if we were going to come up with a classification for all possible lattice types. When we did this, we met Auguste Bravais, who cataloged the 14 so-called Bravais lattices that fall into 7 general classes of lattices. Next, we discussed how pure elemental metals very frequently adopt cubic lattices, so we decided to focus on those. We explored those 3 cubic lattices: primitive, body-centered, and face-centered, noting the increasingly efficient packing as we progressed. This helped us to understand why so many metals seem to prefer this face-centered cubic packing. From there, we turned our attention to alloys, or mixtures of metals. Here, we discussed solid solutions in which atoms or microcrystals of one elemental metal are entombed within the lattice of another. Specifically, we saw how this arrangement of atoms can interrupt slip planes with the host metal's lattice, reducing ductility or malleability, which amounts to increasing hardness. Then we thought about intermetallic compounds, in which multiple metal atoms mix thoroughly on the level of their unit cells, producing all new materials some with remarkable properties like superconductors. We've given some attention to metallic bonding in solids and how it influences their behavior and properties. Next time, we're going to continue our discussion of the properties of solids as we bring ionic and covalent bonds back into the discussion.